Welcome, everyone, and thank you for attending today's webinar, Real-Time Digital Condition Monitoring for Power Plant Optimization. My name's Tom Trappell, and I'll be your moderator. And today our featured speakers are David Thomason, Industry Principal for Global Power Generation at OSIsoft, and Mike Santucci, Founder and President of ECG Incorporated. Today's webinar will take roughly 45 minutes, followed by 10 to 15 minutes of Q&A. But before we get started, I'd like to mention a few housekeeping notes. This webinar is being recorded, and we will be providing the recording and slides after today's webinar. You can expect an email with this content following the conclusion of today's event. Also, if you have any questions for Mike or David today, please feel free to submit them via the Q&A option below on the On24 event digital platform, and we will answer your questions as they arrive. If we're not able to get to everyone's question today, we will certainly follow up with a response afterward. Finally, you could find additional resources for today in the Resource Center at the bottom of your screen. This includes a copy of today's presentation, along with some case studies, and an opportunity to sign up for our next online demonstration of the OSIsoft Pi system. And with that, I'd like to now hand it off to David and Mike to get started with today's webinar. Gentlemen, thank you for joining us.
Thank you, Tom. Yeah, hi, this is David Thomason. I'm Industry Principal for Power Generation globally for OSIsoft. And I'm very pleased to be joined today with Mike Santucci, Founder and President of ECG Inc. OSIsoft leads the market in critical operations. The Pi system is agnostic to industry. We're across multiple industries. Of course, we have some industries we're more prominent in. That would be oil and gas and power and utilities, metals and mining, pharma and life sciences, chemicals, pulp and paper, but we're also in food and beverage, in discrete manufacturing and transportation. Most of these industries have a lot of the common type of things that they do. So condition monitoring and looking at equipment health from a real-time basis as opposed to a post basis or a reactive basis is many of things that all these customers are doing. Equipment's equipment, and whether you're monitoring from a sensor to a piece of equipment to an entire system, the Pi system has been successful across multiple industries. So how do you do this? How do you systematically turn all this data into consumable and actionable information? Digital transformation needs to drive value and results, and we have many customers that are doing so. And that's why we created the Pi system, to be able to have that live situational awareness. So the data has real-time information, it has past information, and it also has future data. This lets you be situationally aware. Also, our tools are designed for you to be able to mine this information. In the past, it was basically just trends. You had to mine and look at your data and your trends. Well, now the tools are built to consume not only the data, but event frames, contextual data, and calculation and results of analytics and such as well. Then, of course, the system is also built to fill any third-party application needs to give it that critical OT data that it may need to run, similar to what our product that Mike will be talking about later. To make that information available to more people, really to broaden the breadth of that information. That information used to be locked down inside the control room. And in this instance, we're opening it up. You're going to make a passive copy of all that real-time critical data now everyone can use. So you're really widening the use across your organizations, being able to get that data into your engineers, into your data scientists, so they can use that in their platforms and in their tools as well, to your maintenance engineers, to the people in the field for remote operations. During this pandemic, it's been critical to get data and information to people who are remote, people working from home or people going to the site, not with their normal crew, but just by themselves and such. To be able to have access to all of that information has been critical during these times, and our tool set allows that to happen. So how does the Pi system work? Well, we have really pervasive data collection, and within this data collection, there's over 450 standard out-of-the-box type of ways to collect data. These are high-speed fidelity interfaces that can bring data in from the speed that whatever you're connecting it to. But we also have interfaces that collect data from websites and do scraping HTML5 or hit a file to pull data from files. So being able to bring all your data together is more than just the real-time data. You want to bring data together that's also your manual data, test data, these other types of things to get a fulfilled correlated type of database to give you richer information. Now that information goes into to be able to be stored and enhanced, and everything in this circle here is one product. It's multiple features, but it all becomes one system, and that's the Pi. And so in the data archives where you'll store that high fidelity real time data, the future data and those types of things, and be able to access to history. Asset framework is a way to organize that information and put it in a way that's better consumed by users and by systems, and we talked about that kind of extensively this morning. And within that asset framework, we can perform asset analytics or real-time streaming calculations, also by marking the database on key events. That way you can mine these events in the time frames that of when they occur, and be able to systematically pull that information and view it and report on it. Also being able to create notifications that go not only to people, but also to systems like for work management and such. And then of course we have to be able to deliver that information, to be able to visualize it, to consume it in Pi Vision or in Pi Data Link, which is an add-in to Excel. We also have OSI Soft Cloud Services and Pi Cloud Connect, and these things are available to take data from a large volume of information, put it up into the cloud, or be able to transfer information from your site securely to a third-party user of that information as well. We also have Pi integrators that let you cleanse, augment, shape, and transmit data from your OT environment of real-time data into more of a relational form and get it into Microsoft BI tools, big data systems, and such to be used by those tools as well. And of course, we have customized access to the information via Pi Web API and SDKs and such. So this is really what the Pi infrastructure entitles, from collecting all the way to delivering and augmenting that information. So there's a triad of digital transformation, and this is where we have people, process, and technology. Now, this concept has been talked about for many, many years. People are changing. We can adapt to more and newer technology now. We should be getting smarter. I'm not sure if we're watching the news lately, if we are all getting smarter, but we should be, and I think we are. Processes change all the time. We're always trying to continuously improve those. But what's really changed in the past 10 years has been this advancement in technology. So by having these techniques and these tools and these ways to do mathematics and such on data is something that wasn't really available in the past, or if it was kind of difficult to do. Now, the intersection of these three, of people, process, and technology, that is really where success is found. And we're going to talk a little bit about some of those technology changes that let you do some of these more complex things that were in the past, but you're doing them very easily nowadays. So I want to talk just a bit about layered analytics approach. And I like to present this because there's a lot of confusion out there and a lot of, let's say, IT hype cycle around certain terms and big data environments and where you can get value. And this is more of kind of an idea of, well, where is a good place to put your analytics? You definitely want them in a place that you can modify them, update them, change them, manage them over time. You don't want a bunch of black boxes out there that you don't have access to really modify what's going on inside. So the Pi system kind of sits in this layer here, in this string analytics and humans. So we're going to get your time and event data and put it into context and such, but be able to actually do real-time streaming calculations and stuff as well in AF analytics and event frames. Let's call that a level 1 predictive analytics. Now, going up a scale, you see people doing tactical machine learning, AI, advanced pattern recognition, strategic, and then community. Tactical would be, well, I'm really using some subject matter expertise to find out exactly what I'll do on a piece of equipment. For this example, let's say a generator. So I'm going to create a model, either machine learning, advanced pattern recognition on a generator. And then by doing that on that piece, I've actually solved a methodology that lets me now strategically apply that across to multiple assets. So once I have that done for one piece of equipment, I can go do that same technique on other type assets. Now at the community level, I'm talking about integrating data into other things, like trying to bring in the information from supply chain and vendors and things like that as well. We also see analytics going down towards the edge. Now, this analytics going down to the edge will happen by having data stores and information available there, maybe even calculations and such. I see vendors and stuff start to produce this. We of course have a product called Pi Data Store, or Edge Data Store, and it allows you to do some of these things as well. Now, the idea of having the IT data lake and the OT structure, we bring those together. We allow you to use IT tools to be able to look at that OT data. When you're talking about the big data lake, the big value adds there is when you can take your OT data and correlate it with other supporting data that you may have in other systems, like maybe your transactional systems in your trading platforms and other types of things. And you really want to see how the fleet performed versus maybe forward positions in power and gas sales and such. Maybe we sold a little bit too much power full forward, and we could have kept some back based on the market, right? So being able to do the circular analysis, that's a good use of a big data system, right? Of being able to get multiple points of data together. But for our purpose of monitoring equipment and such, that sometimes might not be the right tool to apply to analytics, when really what I want to know is, hey, I had a high vibration on that pump. I want a message to come to my phone. I want to be able to look at that data immediately when that happens. Now, that I see happening really in this real-time streaming layer, and also in these top two layers of tactical and strategic, usually done via an advanced pattern recognition program, which we're going to talk about later, or with like ties into machine learning libraries and such. So I hope that kind of clears up about analytics and different places that you can place them for high value. I want to talk a little bit about a PF curve. Now, those that aren't in maintenance may not have seen this, but a PF curve basically illustrates that for every piece of equipment or system, there's a point on the PF curve, that would be the peak point, where some type of degradation has happened. So a piece of equipment or a system is degrading, and this is a point of detection. Then, of course, there's the F point on the curve, which means now that piece of equipment or system has gone to a failure mode. Now, what we can do within conventional systems, they usually alert you more towards the failure, right? Closer, because they're trying to keep things running and operating. They're not set up to be able to catch an early slow failure or a slow degradation, or catching a slow damage like from a vibration bearing or rub. And so by using advanced techniques, you want to be monitoring these sensors, monitoring these things in a way that you can alarm on changes, that you can do rate of change calculations, that you can do pattern recognition. The idea is to move as far up this curve as you can to detect something as early as possible, and that gives you an opportunity time frame that allows you to plan the work, to plan the labor, to schedule an outage for your facility, to really plan the entire activity around how you're going to do this. Now, this needs to result in a circular learning around maintenance. And when we look at maintenance, this kind of is a target goal for large industries, and this was from a study years ago. But it basically found out that the average plant performs around 55% of their maintenance is reactive work. Now, this reactive work is the highest cost because you haven't planned for any of these things, right? You're just waiting till something breaks, and now you're out of the market, you're out of the money, and you're having to plan to repair the device. You may have to go buy replacement power in the power generation industry to put power back on the grid, and then you still have to go fix the equipment. But the study also showed that there's top industrial plants that actually perform around 10% or less reactive, and they did that by enhancing and using data and analytics systems. So they're really using information to drive decisions, right? And so the idea here is, as you start to use more information and more data and analytics, you're really driving up your predictive capability in your work orders, right? So you're doing work because you're detecting things early. Now, on the preventive side, you're not really reducing preventive. In fact, you may have to increase preventive in some areas, but what you're really is optimizing preventive around a condition-based strategy. So condition-based strategy doesn't mean I'm just moving things from a time-based system, right, to exactly hours of run and operations. It's when I do run a certain amount of hours and a certain amount of start and stop counts, I'm also looking at, well, what's the condition? Is it still good? If it's still good, maybe I get 500 more hours out of it. So what you're doing is you're optimizing your preventive maintenance, and by doing both of those things, the end result is to drive down maintenance that you're doing based on reactive work. An idea around this is in electric motors, we started early detecting of, just the winding temperatures going up on the motors themselves. So you change your maintenance practice to clean them quicker and sooner, and that way you never really have any winding temperature damage or any related bearing damage as well. So you want to optimize your work order type of system. You can actually code work order systems to have these in there and track the improvement of plants over time as they adopt the technology and deploy a digital strategy. You're talking about the pie system. Simple kind of decomposition is that you're really going to gather the information in the pie system. You're going to collect it with those interfaces and ways to bring in data and information, all your real-time data, and correlate all that information together. Then you're going to transform some of that information into these calculations where you're getting efficiencies and design versus actuals, and rate of change, and these types of things. And you do that in the real-time data stream. And then, of course, we can do more CBM type level things. We're talking about volumes and time and service and such. And then, of course, being able to consume these either by registering and running some KPIs within the calculations, doing reporting against these things, or feeding it into other applications. All that functionality can be done right there within the PI system. And then, of course, to tie that PI system into a work management system like Maximo, SAP, Meridian, or also tying in for another level, for that level 2 analytic, an application which is a bolt-on, like advanced pattern recognition or machine learning type of application that allows you to get even more insight to these assets. So that's basically kind of what that would look like under a construct under PI of what CBM would look like. So let's talk about asset framework. Asset framework is a way to be able to structure your information and then consolidate more data into it. So basically, it's an object model and an abstraction layer. And the abstraction layer is both for users, ease of use, and then also an ease of use to getting data into other applications as well. But you're bringing in your real-time data series, you're bringing in all the information that you can get out of your DCS, your control systems, vibration systems, all those types of things. And then, but you can also bring in some nameplate data, right? Some information that may be coming from your work and materials management system. Sorry about the slide problem. We can calculate these efficiencies and performance indicators and doing downtime, startup failures. We can do all these types of events that'll show the startup of a gas turbine and the shutdown of a gas turbine, or the variations within what's going on in other type of generation assets. We can turn those into notifications as well, and reference performance curves and limits and things. And anything you get in the abstraction layer and in that model, then you can do mathematics on those. Now, let's talk about what that means. It means that we're connecting to all of our raw real-time data. We're going to put that into a structure that makes sense and is consumable to the users and puts the data and information in areas that make sense, like all the data around a pump, all the data around a generator, and we can consolidate that information so it's easier to use and find and easier to do that mathematics. Also being able to reference those other things that you do. Now, once you have all your raw data in a structured data, now what we can do is use those event frames and analytics and change and create new information, transform that data into more consumable stuff. Like, hey, I'm taking like an amperage or a flow and I'm turning that into, I know that pump is on or off. So I have a start and stop counts. How many times does it run? How long has it been running? I can have this systematically be recording into the database. And then all I need to do then from a reporting perspective is mine that information. I can move the data screens around per those timeframes and such as well to do ad hoc analysis. I can do things like rate of change calculations. So if I have, a generator that only heats up at a certain amount from start to on, but I start seeing it heating up at a faster rate, I can have that send a notification to me. Doesn't mean it's hot yet. It just means it's getting hotter faster than it normally does. I can compare actual versus designs. There's all these things that we can do in that layer right there in the real-time data stream itself, and be able to do these calculations, and of course, in being able to get notifications on those, bring that to the users who need, or also bring that information out to another system. So now I have my structured data. I still have access to all the raw data as well. I don't lose any of that, and I have these transform results. That's where I'm going to get most of my bang for the buck there. But then I can also tie this into other systems, right? I can send that data into an APR or into hooks with R and MATLAB and Python and such, or get it into big data systems via our integrators and be consumed in other ways as well. So we do this in AF through smart objects, what we call templates. So these templates you can create per like equipment or per system if you want. And then as you use that template across multiple assets, I then now can take that, and if I modify, let's say we have a new mathematic on this generator template, and I want to add it. I can add it to that one. I can test it, see if it's doing what I want it to do, and if I like it, I can say, you know what, apply that mathematic to every generator that I use the template on. Now you can imagine if I'm managing, 6,000 wind turbines, right, with generators in them, and I want to apply a new mathematic or a new notification or whatever, how easy that can be now once I can do this idea of smart objects in AF to apply and accept new modern change. And so I basically can build out my plant, my asset, my wind farm, my solar park, and then I can do that to multiple sites and end up building a whole view of an entire organization. Now, when we're talking about this data, we're always looking at a focus internally, right? So we're looking at, are we monitoring the heat rate and equipment site performance? Are we looking at, we should always be focused that inside the asset, it's technically working as well as it should. And this could be your solar inverters, your combiner boxes, measuring all the way down to panels and strings, really looking at the assets from the inside. And then you can do all that by that modern technology. So you have the raw data, but then you also are going to groom that information, create that new data for them, and enhance that information to make this better decisions. Now, one thing else that kind of drives your maintenance strategy is, of course, your financials. So not only do we need that focus internally to all of our assets, we need to step back and say, you know what, there's other data, there's other information that we need to put around this. And this would be like around, what does it cost? What's my fuel? What's my permits, my consumables, my maintenance, my contracts I may have? What are these things that are the cost of that facility? And then at the same time, what are the things that I have for revenue on that facility? Maybe it's in the market live and I'm getting real-time megawatt hour payments out of a market, or maybe I have a PPA contract. I just need to measure my performance versus the terms of my contract. We have customers that are doing that with NAF, where they're actually measuring how they're doing against their PPA rules and displaying those in near real time on their dashboards and being able to see exactly where they are in compliance to that. Same way with regulatory as well, making sure they're 100% compliant with regulatory issues, whether they be environmental or operational. Being able to look at and calculate the value of some of these ancillary type services when you're doing things like voltage support or automatic generation control and those types of things. You need to get your hands on those so you really can understand how that can help drive what maintenance you should be doing and on what assets. Uniper is one of our big customers over in Europe, and they were able to combine all this information to be able to look at things in ways that by using analytics driven by their maintenance planning tool that incorporated their commercial data, they were able to reduce their CapEx spending by 16%. A quick example of e-monitoring performance using Pi event frames. This is from EDF, monitoring site. Just an example of a pump. So they had this pump in operation since 2011. They wanted to see what the maximum vibration was overall that time that's there. Now, having Pi, our calculations and event frames can be back calculated. So as you create one now, you can say, you know what, I've had Pi running for a couple of years. Let's go back in time and build that same event frame or build that same calculation. And here's what they did on this pump study. So they're able to go out there, build the event frames, back calculate those, and do a pump study in less than two hours. Now you think about trying to do that in the past, this would have taken a long time to do. These guys were able to do it in minimal time. And subtle engineering, it monitors a diverse fleet of of assets. They're out of Italy, and they also have a center in Florida as well. And they monitor gas turbines and HRSGs, and they monitor plants from all over the place. They have taken this to heart. They use AF for their asset modeling. They use notifications to get information out to the right folks. And they're also using event frames for their asset and analytics as well. And they're using Pi Vision, which is our visualization tool, which is based on HTML5, and they use some extensibility features of it as well. Just some examples of some high-level screens. This is a one-glance look at a bunch of gas turbines. Of course, there's some calculations behind the scene to determine what their condition are at this point, but they can drill down into these various processes, looking into the gas turbine production itself, its exhaust temperature spreads, those types of things in details, being able to look down into their generators and study those, being able to look at their steam turbines and such, all with the same system, all with the same visualization tools that work on your phone all the way to your desktop. Now, this story here I like to hype on because this is done. This is Australia Gas and Light down out of Melbourne, Australia, and they really were aggressive and quite a success at doing a digital transformation. They began really growing their fleet quickly, and around 4 or 5 years ago, went into a digitalization move with OSI Soft. Basically, their footprint of IT is quite small to do the accomplishments that they've done. They're using core Pi products. Pi is in its center of their operation technology center, and they're using these features of AS, and they're using Pi Vision and Process Book and Manual Logger to collect all your manual data in rounds and such. And they're using ECG's Predicted, which is Mike's going to talk about it right after I speak here. And so, as you see, their footprint is quite small from an IT landscape perspective. They really drive events down into a logbook, also a partner product called RT Tech software. It's RT Duet. They're doing some event frame analysis there, but then they can also drive work orders and information back into their SAP system from either J5 or directly from the Pi system. I'd like to show some of these things that they were able to accomplish in minimal amount of years. So they're monitoring the condition and the health of solar facilities. They're monitoring the real-time process of their water systems and such. They're monitoring their chemistry. One of their chemists took the training, took to it, came up with this beautiful screen. They've now applied this to multiple sites, and people can access this on their handhelds as well. They're looking at their generator monitoring. They have some remote hydros that are very far away, like over 700 kilometers away. This was one of their craftsmen had put together a really nice set of tools to monitor the trips. So when they have a trip at one of these units, they know what to dispatch out. Various things like generator capability monitoring, feed pump performance, total fleet capacity, environmental monitoring, and of course collecting data up on a mountain on a snowmobile basically is future data they could put into the system, because this is future water reserves, basically a fuel for the hydros that's going to come down into the reservoirs, so they can measure the depth and the density and put that into their calculations for what they have capability of on their hydro units. Now, this case here I want to talk about is a very significant catch that they made. It was on a 560 megawatt hydrogen cooled stator. Basically, this unit had a little temperature drift. The Pi system with pattern recognition noticed that drift. They decided that, hey, that we need to start looking at this thing closer. So they started watching it. Sure enough, later on, it spiked up a little bit more. It's still not a temperature that would set off a lot of alarms or anything, so everything looks good, but it's higher than it should be. And they decided, the central engineering group working in cooperation and partnership with the local plant site, decided to do a detailed inspection and really look at this unit. And sure enough, it was very near catastrophic damage and thermal runaway. If it would have gotten worse, this thing would have been a 12 to 14 week outage. It actually only took them about 4.5 weeks to fix this part of the generator, and it avoided possibly $50 to $70 million in losses. by being able to do that. So just over the past 3 years, AGL's had some great results. Over 18.7 million in avoided losses in three years, 8.5 million from the financial savings last year. Now this was from 2018, and those savings don't include this one big one of the 50 to 70 million on that generator. So I'd like to pass this on to Mr. Mike Santucci of ECG, and he's going to talk to you about what they offer and how Predictit played a role in that. Mike?
Hey, thanks a lot, Dave. And thank you, Tom. I'm Mike Santucci from Engineering Consultants Group. I'm going to talk in specifics about our product Predictit. This is an APR product that bolts onto the OSI soft PI system. I'm a mechanical engineer, 35 years in the power industry, and been doing things like controls and monitoring systems pretty much all my career. This product that we'll talk about here is another big data analytics type of program, and there's certainly a lot of hype, as Dave had mentioned in his presentation, around putting analytics to this data that we're collecting. Some of the stats that I have here is, 92% of Fortune 1000 companies are doing something, increasing their investments in big data and analytics. And the market's projected to increase or to double in the next 7 years. So a lot of momentum here around these technologies. But one caveat here is that the statistical reports that 50% of predicted analytic projects are reporting very little or no return from the investment. And so the focus is on how do you get your investment to pay off, and what's the quickest, where's the low-hanging fruit, where should we focus most of our attention? And that'll be the theme of this software. So Predictit is an advanced pattern recognition system. To describe where it kind of fits in the overall PI stack. We are very PI centric. The bottom layer of what Dave described here is configuration of hard limit alarms, utilization of PI-AF for analytics and so forth. We're a layer basically above that, where you're trying to organize information, bring multiple sensors together, and try to get some sort of meaning or value out of multiple sensors. And the purpose of that is for this anomaly detection. How can I use the information around an asset to let me know where each of those sensors should be for each load that I happen to be at? Above that layer is what you want to do with the alarms that would come in with the system. So I found an anomaly, something's going on. What could that mean? How does that map to things that I already know, or failure mechanisms that are typical for this kind of an asset? This is the third level of our software here in the reasoning and the diagnostics around analytics. So Predictit, we start out with building out an advanced pattern recognition models, and the very first step in that is the deployment of the models, and then we move on to the anomaly detection part of the software, where we're picking up slight changes in the process, and then moving from that to causality. What does this symptom indicate? What's developing, and how do I organize that? How do I take these typical faults and figure out which symptoms are indicating what might be happening? And then finally, the take action, and Dave spoke to this, that all this is for naught unless there's a way to close the loop on the identification of an anomaly and communication to the plant for action. So we'll start with the advanced pattern recognition and kind of build up to where we want to go with the diagnostics. So in our APR, and most all APRs are like this, there's a subject matter expert that's kind of needed to put a context around what information kind of belongs together. So in my example here, I have a fan that I'm trying to build a model around. And of course, these fans, they move from a low load to a high load, and as they move, the temperatures, pressures, flows, damper positions, the amps, they all kind of move up and down along with the asset. And what you're trying to do with the APR system is capture that information, the information that one sensor contains about the behavior of the second. So in the first part of the build out of the APR, you're doing a tag mapping, you're trying to figure out what data belongs together. The next step of the advanced pattern recognition is what data do I use to train the model? And so the PI system is rich in historical data, so I have a lot of information that I can use. And again, a subject matter expert is kind of useful in picking out what are the training periods that are free of anomalies and free of sensor issues and so forth. And so we have a mechanism to grab data from the PI system, from the archive, and that becomes the basis. That time series slices of data becomes the basis for what we will consider to build a model. And so with that information then you need to massage the data. So there'll be sensors that have no values that you need to do imputation on, and other sensors that are out of range or that you want to exclude. So this filtering mechanism or outlier removal method is a very big part of building the models. If you build good models with steady state information, they'll be very repeatable. So in this process of building out the models, we spend a lot of time and analytics on coming up with the right data to use to define the normal operating behavior. Once we have this normal operating behavior for each of the models, then we can use the information that we retain and the relationships between the variables to generate expected values. So in this example, if I want to calculate the flow in the upper left or upper right, I'll use the pressure sensor and the temperature sensor and the amp sensor in this case to determine where the expected value is. And the expected value becomes some sort of an average of the data or the other points that are in the model, those with higher correlation having more weight on generating the expected value for the target variable. So this feature extraction, grabbing all this data and trying to figure out where how the asset behaves for every different load is the basis of the APR. And so we're generating an expected value for every point that's in a model and then trying to use that to figure out when things change. So by building out the models, we generate a tolerance by which we can calculate the expected value. If we have very good, tight correlation between sensors, the tolerance band is very small. If the correlation is not so good, we can't figure out what the sensor is doing, the tolerance bands get larger and larger. So those are things that get calculated automatically right out of the box with the software. But once these tolerances are built, then we can apply these to the sensors and then be able to determine when a sensor is outside of its normal operating range. And at that point, that's the trigger for an alarm in our system. And the thought here is that you have these alarms that can come in when there's a slight deviation in the process. We're talking maybe 3, 4, 5% over the range of the normal operation of the sensor being able to detect that kind of a deviation. And again, the early warning that you get as a result of doing this is the value proposition of the software. Being able to determine this months ahead or weeks ahead so that you can plan it rather than react to it is where the value is at. So what we do then with the anomaly is we want to move up the chain. We want to move, okay, what is this anomaly? What is the alarm associated with? And so we take the anomaly and it would map into multiple models for different fans in this case. But this asset variable called bearing inboard temperature, we want to look at its behavior to figure out what it's telling us a likely fault might be. So if we look at this inboard temperature and we look at its behavior and it's deviating high, we want to be able to map this to the common problems that this asset type might display. So in this case, inboard bearing temperature deviating high would be associated with a bearing issue. So this is a simplified example, but this is basically how this diagnostic piece works. And again, we bring the subject matter expert back in to do what we call the knowledge elicitation. How do we figure out what problems an asset type has, and how frequently do we have that kind of a problem? And this we may employ multiple SMEs. That one that's a fan guy, one that's a pump guy, one that's a turbine guy. But we compile these lists of typical types of failures or faults, and there may be anywhere from 10 on a simple asset to 50, 60 on a steam turbine or a gas turbine. And this information can come from the knowledge of a single person or multiple people, and combined with a fault library. So if you have a database of, hey, the fan failed, we had this failure and we saw this symptom and that symptom, we can ingest that kind of information to build a diagnostic network. So this diagnostic network is basically a mapping between faults and symptoms. Okay, so if I list out all of my faults here in the top part of this display here under faults, and all my symptoms at the lower part, I can see that when I have a problem with a damper shear pin, for example, on this fan, I'm going to see the symptoms of an airflow deviation, discharge pressure deviation, and probably a damper position deviation. And they may have more weight. So this probability of seeing a symptom given the fault is something that the subject matter expert sets up. And he sets this up one time for the asset, and then this network then can be applied to any asset that falls under this asset type. So this configuration of faults to symptoms, once we do this for the rest of the faults there, we form a network, and we call this network a causal asset network. And we would have a causal asset network for a fan and a pump and a steam turbine and so forth. And this configuration of this asset, with all the knowledge of the subject matter expert, combined with a database of faults, basically becomes our fault signature database, or a network that allows us to reason. So a typical network for this is for a cold pulverizer would look like this. We have a middle layer here that contains our common faults for a pulverizer. The layer in light blue would be the pi-derived symptoms. So mill temperature going high or going low, the amps high or low. These are all pi-derived APR alarms. There's also the need to ingest additional information from what we call tech exams. This would be like a fineness test, acoustic test, oil analysis, and so on. So the results from these tests are also very helpful in distinguishing between common faults. And we can basically want to ingest both the APR-derived symptoms along with the tech exam symptoms. The end result is this interface, the GUI for our diagnostic reasoner. And in the diagnostic reasoner, the upper left-hand corner then would list out all the possible faults for the asset. And then down below it would be all of our tech exams. So these are the manual things that would come into to play as symptoms. And the lower right-hand corner would be all the pi-derived alarms that are possible. And when those alarms come into play, they move up into evidence. And with this evidence, then we calculate the likelihood of each fault being present. So in this model, we're using something that's not conventional, where it's like a fishbone diagram that you go down and you get to a root cause. This is saying that all faults are possible, and we're going to rank the faults by the likelihood, the frequency that we see these kinds of faults, and then we're going to change our mind about the likelihood given the new evidence. So every time a piece of evidence comes in from these ranked observations or from a tech exam, this is a PM, this information goes into the reasoner then for the specific asset and lets us know the likelihood of what problems might be developing. So a couple examples of what we've just described here, and Dave spoke about the AGL generator, and this is a generator to another utility. I happen to have two generator examples in our presentation here. So this is a water-cooled generator. The stators are water-cooled, and this example, we have an oxide buildup inside one of the passages that built up over time. The operator's first acknowledgement that there was any kind of issue at all was an alarm 12 hours prior to the trip. So we took this information as a post-mortem to try to see what APR would have been able to show. And when we run this data, we included data from up to 3 years. I guess it was 3 years of data. We included the first year as our training data and then tried to predict out what would happen over the course of the next 2 years. And we were able to detect an anomaly here. You can see where our two lines start pulling apart, the green shaded area representing the anomaly determined. And, the end result here is that, they had a planned outage in this window here that once you see this anomaly, if we would have reacted to it, we could have done an acid flush or whatever and possibly removed the buildup, but we didn't, and we ran for another year before the insulation broke down and the generator tripped the ground. So this was a very costly, as you can imagine. This is 900 megawatt unit that came down unexpectedly. In this second example here, I'm going to try to describe the APR and how the diagnostic reasoner works together. So in this example, we're going to talk about a coal pulverizer. This is a nasty machine that grinds coal between the table and the rolls. And in this case study here, one of these the seals on one of these rolls gave way and allowed ash and coal to get down into the rolls and worked on the bearings over time and eventually seized the roll up. So what we saw in the APR software was this roll bearing failure. Here's some of those inputs on this model. You can see, I don't know if you can read this, but the bottom trend is the amps, and we first see an alarm on the amps. We can see when the roll actually physically seized up back in here. And so we're seeing an alarm on the amps 3 or 4 days before this. There's another alarm that happens on the roll deflections here a day after the first indication. And so as this information comes in, we're notified prior to the imminent failure here. The diagnostic reasoner is trying to figure out what's going on. So the very first piece of information that we get is this deviation in the millamps. And with this one piece of evidence here, it's sorting through all the possible faults and then ranking them based on likelihood. And in this case here, we're guessing that it's a broken spring, but we have low likelihood, low probability that this is actually the problem. But we're focused in on the top 3 issues as being the likely problems, and we can use this information then to figure out which ones of our tech exams are the most valuable to run to help us solve these problems. So in the next piece of evidence comes in, the roll deflection. Now we're recalculating the network. We have a different likelihood for each of these failure types, and we're thinking, okay, it could be a mill worn condition, or a roll seized condition, or a feeder problem of some kind. So again, as new information is coming in, we're rethinking and recalculating, forming new opinions about the likelihood of what faults may be present. So in this example here, the tech exam that had the most value was, is there pyrites or coal in the pyrite chute for this pulverizer? And between that and then the additional piece of information, another roll coming in, we have now new information, and we have roll seized as our likely fault. And so basically, given this evidence here, we are basically determining how likely we are to have these fault conditions present. And at some point, you go over some threshold and you say, okay, I'm pretty sure that this condition, this roll seized condition exists. So this is the basis of this diagnostic reasoner. And we're basically building out these causal asset networks for all common power plant equipment. We have them for the steam turbine and the gas turbine, air heaters, fans, pumps, and so forth. So we're trying to build these things out and come up with a community that can utilize these resources. So our customers here can take this and share the fault information. So no one customer has to see all these faults for the network to have the information of the collection. So these are some of our customers that's listed on this screen here. We are the predicted APR software and diagnostic reasoning is applied to about 90 gigawatts of power across the world, most of it here in the United States, but we have some installations abroad. So, the takeaways of this this presentation here is pretty much, you need a robust, stable solution to deploy these models. Okay, a simple plant may have, simple one unit may have 30 to 50 different models. And this is all critical assets, the steam turbine, the generator, pulverizers, fans, feed pumps, those pieces of equipment that'll impact uptime. So you need a scalable solution. All these solutions that, and even in our world, we start with MATLAB or Python, and we build out these analytics, and then we put it into a form where we can scale it up. So we have customers that with just 50 models, and then customers like Dave was talking about, HEL, that probably has 4,000 models. So they have a big fleet, a lot of equipment, and so a big scalable system that allows them to deploy rapidly using the AF infrastructure, and then also administer it, applying alarm limits across the entirety of all the models and so forth. So this targeted analytics is kind of a takeaway here. Be critical asset centric in terms of deployment of these models. You're looking for little disturbances on these critical assets as a telltale of what's happening. And then once we have the alarms, how do you categorize that information into what the common faults associated with that asset type? That's what we're building out here now. Of course, having the PI system down below us and leveraging everything that's all organized for us to be able to go grab information to build models rapidly with, it really helps us, deploy this rapidly. I think that's my last slide here. So I'll turn this back over to Dave and Tom for some question and answer, I guess.
Well, thank you, Mike, and thank you, David. Okay, folks, at this time, we're going to take questions from the audience. Once again, please feel free to submit your questions down below via the Q&A option on the On24 digital event platform, and we'll answer your questions as they arrive. If we're not able to get to everyone's question today, we will certainly follow up with a response afterward. And why don't we just get started? David, this first question is for you. In reference to vibration data, are you collecting raw data or static and dynamic data?
You can collect the raw data. Of course, I always tell people to interface their vibration systems into the PI system. You normally can do that, whether it be a Bentley system or Emerson type system. Usually you can get at least second data into the PI system, but you can also do more than that. We have other partners like SetPoint that actually have made connections into the PI system with their hardware and such, where they're bringing in the very high fidelity data and even doing the spectral analysis as well. You're not going to get that everywhere, right? But if you get the XYs, you can use that as correlated data in these models, as Mike alluded to, because it's great information to know that vibration also is at that level when the RPM is X, or when the amps is X, and when pressure flow is X. By having correlated data together, it enriches the model and lets you do earlier anomaly detections. So yes, get your vibration data in there. There's multiple interfaces that can do it. I think with the Bentley systems, we were using like a Modbus interface to bring in the data at a second or less. So I hope that answered the question.
Great, thank you. Mike, this question came in during your part of the presentation. If a piece of equipment is not performing per design and you build your model based on this poor performance historical data, how good would be the APR monitoring?
That's a great question. APR is a statistical approach. So it's not based on first principles. We're going to basically build a model around whatever the sensor is telling us. So what the APR is great at is being able to detect a change. So if we build a model around a sensor, let's say a pressure sensor has a calibration issue in it, and it's reading 5 psi low. we'll learn the behavior of that particular sensor for that particular asset. And we'll say that 5 degrees low or 5 psi low is normal. And if they go and calibrate that sensor, it'll generate an alarm in our system saying, hey, we have a problem. And then at that point, we can bias up our expected value to meet that. So we build based on statistics alone. These are all empirical models, based on what we have accumulated in the Pi system. There's still great value in being able to do that, even with, not the exact value, but a value that's moving up and down as it should with the process.
Yeah, hey, Mike, if you don't mind, I'd like to add in on that as well. So I used to get asked this in my previous company when we rolled out models as well all over many assets. And there's like, yeah, if I'm going to model a known condition, at least I will know now when that condition is going to change. So if I have a small rub or a crack like in a bearing or something, and I model that into my model, it will detect for surely when it gets a little bit worse, right? So you'll still get early detection of things that aren't designed perfect, and that's kind of the point of using statistical, because you're measuring against the pump you have, not just versus a design of that equipment. Go ahead, Tom. Sorry.
Yeah, no, this kind of follows into the next question here. Is it possible to integrate spectrum vibration measurements into APR models or decision trees? For example, wind turbines have continuous vibration monitoring systems.
Yeah, is that for me? Tom, I'll take it. I'll take the first half of it, and Dave, you can have the last. Yeah, the spectral information is very valuable, and if you have it, you should use it. If you have the waveform and you can, Fourier transform it and pull out the peak amplitudes and frequencies, you can narrow in on different type of failure modes. So you can tell the difference between an imbalance and a misalignment with a different component within the frequency spectrum. So yeah, bearing frequencies and so forth, they all lend themselves to specifying what kind of a fault. When you have a vibration problem, is it in the bearing? And it basically further allows you to delineate out what the problem might be.
I think anything I would add to that would sound like big crayon use. Big good, Mike.
All right, gentlemen, this next question is for both of you. It's a two-part question. Is the actual implementation of the analytics and where the analytics are inserted covered in the Pi Analytics class? Secondly, is there a forum or resource for general or industry-specific Pi Analytics routines?
So to the first one, I'm sure that our Pi Analytics class covers not only the use of event frames, the creation of them, but also in calculations. So there's many type of calculations that you can do in the streaming analytics world. And then also even what we call a roll-up type of calculation if we want a value to basically transfer up the asset framework structure. So yes, you will learn those in a Pi Analytics type course. The second part of that question, I'm not sure of.
Yeah, on the second part of the question, we did participate in a CBM class that OSI Soft had at the user conference 2 years ago with Keith Pierce. But we have our own training videos and so forth for learning the APR.
Great, thank you. Mike, how long did it take for you to develop the process and place this into production?
You mean to deploy an application of PredictIt? Is that the question?
Yes.
Yeah. So deploying the application is fairly simple. The most time is involved in doing the tag mapping, figuring out what sensors go with a pump or whatever. If a customer has an AF built out, all of that legwork is done. And so it's very easy for us because we can take in not only Pi tags, but AF attributes in our models. And so if the organization is done up front to roll out a typical, coal-fired power plant unit, it's a matter of a couple of days to do that. 30, 40, 50 models, depending on the complexity there. It's a couple of days worth of work. We have automated routines inside of our software. So you can walk through these processes of building models, removing outliers, and defining what kind of machine learning to remove the outliers, to apply, or you can do it yourself. We can do it automated, so it can be done really quick. Most people have a hybrid of using the automation and checking it themselves when they're building the models.
Great, thank you. Our next question is again for you, Mike. How many samples for each pi tag are you typically using to calibrate your APR model? For example, 5-minute data over the past year with using specific operational filters.
Yeah, so just kind of rule of thumb, you have to build models with training data that covers all the operating states. So covering all the operating states is kind of a broad statement. If you have an asset that's, say, a fan that's running outside and it's impacted by seasonal effects, then you may need a year's worth of data to find out all the temperature swings, temperature and humidity swings that would impact what the bearing temperatures may be. On the other hand, if you have a fan or a pump that's running in a controlled environment, you may only need to see that fan or pump for 3 or 4 weeks to capture all the possible running states and multiple startups and shutdowns and so forth. So it varies, but basically you're trying to capture the different steady state conditions. And if that happens over the course of a month or 2 months, then that's enough data. If it's something that's broader or weather impacted, you may need up to a year's worth of data. And the year's worth of data, you're probably taking it at, say, an hour interval. The 2-week type data, you may take it at 10-minute interval.
Great, thank you. Folks, we're coming up to the end of the hour, so we're just going to take one more question. If we were not able to get to your question today, we will certainly follow up with a direct response afterward. And so the last question we're going to take, Mike, about PredictIt. Have you got models for pre-configured or different asset types and the root causes for these failures?
Yes, we have some of that done. The APR we've had for years, and it's stable and very mature, and we have some templates for building out common equipment. The asset networks, the causal asset networks, we're building that out here now. So over the past year and a half, we've been building assets. As I said, we have a steam turbine, a generator, gas turbine, pretty much the combined cycle major equipment's defined, and we're working on now OEM specific stuff, a B&W pulverizer versus a combustion engineering pulverizer and so forth. So we have probably 20 different asset types built out, and our goal here is to build out most of the common stuff here by the end of the year or into the middle of next year.
Great, thank you, Mike. All right, folks, I apologize. We have run up to the end of our hour. If we were not able to answer your question today, we will certainly follow up with the responses afterwards. And if you do happen to have additional questions following today's event, please feel free to submit them from one of our direct responses following today's webinar. Once again, thank you for attending. And Mike, Dave, thank you for your presentation.
Thank you, Tom.
Yeah. Thank you, Tom.
Take care, everyone.
All right.